Hello students, let's continue from where we left last time. So in the last lecture we discussed about the constraints that space-time symmetries impose on the kind of forces that we can have. Okay, we saw for example that time cannot appear explicitly in the forces. Okay, and that's true if your system is isolated from all other things. I mean, if your system is not influenced by something external. Okay, if that is not the case, then of course the forces can be time dependent. But if you have isolated system, then the forces which are acting on individual particles within the system are not dependent on time. Also, you saw that that the forces cannot depend on the absolute locations of individual particles. Okay, they can only know about the relative separation between the constituents. Okay, and similarly, you saw that that the fact that physics does not change in going from one inertial frame to another inertial frame implies that those forces cannot depend on what the velocities are in a given reference frame. They can only depend on the differences in velocities of different particles. Okay, so that was our first experience with the use of symmetries of space and time, and we will have more occasions to do these things later as well. Now today we want to proceed by looking at the coordinates that we have used more carefully. Okay, so till now I have been, whenever I have been speaking of where the particles are located, I always assumed that the coordinates are Cartesian coordinates. Okay, and for us there was no reason to use any other coordinate, and that's why we use Cartesian coordinates. Okay, so now we want to talk a little more about coordinates, and that's what the plan is for this short video. So what I said just now is that till now we have used the Cartesian coordinates. So if I'm specifying the configuration of the system, okay, of system, okay, I was using the coordinates Ri. Okay, and by this Ri I mean xi, yi, and zi. Okay, it's clear that there may be situations when using Cartesian coordinates may not be the best thing to do. For example, if you are looking at, let's say, a planet which is going around sun in a circular orbit. Okay, it's clear that it's not such a useful thing to do to use x, y, and z components to tell where that planet is located. Okay, it will be more natural to use the polar coordinates. So you would use, for example, the radial distances away from the sun, the polar and azimuthal angles. They will be more natural coordinates because they know about the symmetry of the problem. See, the force which is acting between the sun and the planet is central. Okay, meaning it depends only on the distances between these two objects, the sun and the planet. Okay, so you want to use a coordinate where this symmetry becomes apparent, and clearly using your polar coordinates will be more useful. So one reason why you may want to use a coordinate other than the Cartesian coordinates is purely the symmetry of the problem. Symmetry of the problem may dictate, for example, use polar coordinates, okay? Or it may say, okay, you should use cylindrical coordinates. Cylindrical coordinates. So that's one simple way of understanding why you might be interested in different coordinates. There's another reason why you would like to use coordinates other than Cartesian coordinates. Imagine you have one particle, okay, and that particle is moving along a specified curve, okay, meaning it can go, let's say it can go only, imagine a thread here, imagine a thread being given here, okay, and you say that your particle can only trace this thread. So it can always be on this thread, and you have already told the way in which that thread is placed, okay. And there may be certain forces acting on this this particle. It might be getting pulled and pushed by other things, but it still always remains on the thread. Now, is using Cartesian coordinates a useful thing to do? Well, that would be an overuse of things, because you don't really need to tell where, to tell where that object is located, you don't need to tell three numbers. You don't need to tell what the x coordinate is, what the y coordinate is, and what the z coordinate is, okay. Clearly it's an overspecification. What you need to tell is how far along the curve it is from some chosen point O. So you choose, let's say, let me draw it, it will be probably easier to understand. Let's say you are given some such curve, okay, and you have your particle sitting here, and this guy is moving along the curve. Now, if I want to tell where it is, let's say I choose some point as a reference point O, and if I tell, okay, go along this curve for 3 meters and you will find the particle. That one number, 3 meters, is sufficient to tell where it is. You don't need to tell me three numbers. You don't need to tell me x, y, and z, okay. So clearly, if you are studying such a system, you don't need to use Cartesian coordinates, okay. Let's call the distance along this curve to be q, okay. That's the notation I will use. This is your first instance of using a coordinate which we call a generalized coordinate, okay. In this case, it is still a distance, but we'll see more examples where a generalized coordinate may not even have the dimensions of length. Okay, so I hope you understand that it may be more natural to use other coordinates rather than Cartesian coordinates. Okay, I'll give you another example. For that, I should go to next page, which is here. It did work, yes. Okay, look at this very commonly used example. Yeah. So there is some ceiling, and from that ceiling you have suspended one pendulum, okay, and from this pendulum, this bob, this mass, you have attached another pendulum, okay. Now my system is these two masses, okay. I'm assuming the strings to be massless, weightless, and massless, and they are just there to support the masses. Now I ask, how many numbers you should tell me to tell exactly where those two particles are located, okay. Now you may say, okay, we need to specify, let's call this particle 1 and particle 2. So they have the masses 1 and 2. So very naively, you might think that I need to specify x1, y1, z1 for the particle number 1, x2, y2, z2 for the particle number 2. But again, this is an overspecification. You don't need those many numbers. Okay, let's say these two masses are really doing whatever they do in the plane of let's say this whiteboard. Okay, so they are always in the plane. Clearly you don't need the Z1 and Z2. They always remain the same. They always remain 0 if you choose them to be. But even then you don't need x1 and y1, x2 and y2. Okay, let's see what you really need to specify. Okay, if you tell me this angle theta 1, if you tell me that one, I will know where this guy is. I will know that because this length is not going to change, so I have to tell you the length. If I don't tell you the length, you cannot know where it is. Okay, so this length of this first string doesn't change. Let's say L1, and look at the particle number 2. So this is another vertical line. So what I'm saying is, from the bob number 1, you draw a vertical line, tell this angle theta 2, and you will know where this M2 is, because the length L2 from this to this is also going to be specified to you. So you see, this, to specify the configuration of this system, you need only two numbers, theta 1 and theta 2. Let me write it down. Configuration of the system. Okay, and this one needs only theta 1 and theta 2. So this is another example of generalized coordinates. So instead of 6, or instead of all these 6 or even 4, by if you tell Z1 and Z2 are fixed, you still realize that the constraints of your system impose restrictions, which leads to the fact that only two coordinates are independent. Okay, so what we say is that this system has 2 degrees of freedom. Okay, 2 because 2 numbers here, which means that these are the independent coordinates. Okay. Now you see, you may say, okay, I don't want to use theta 1 and theta 2. I want to use some other combination of theta 1 and theta 2. That you can do, of course, but that will not change the fact that you still you need only 2 independent quantities, 2 independent numbers. So whatever transformations you do, you will still realize that only 2 independent coordinates are required. The minimum number is 2, and that is what is called the degrees of freedom of this system, or any system which you are looking at. Let's look at few examples. Okay, my plan was to give you a few examples as an exercise. Okay, they are very, very simple, and I will write them down. You think about them, and then one after the other I will tell you the answers. Okay, so let's do that. I'll go to next page. I hope it goes. No, it doesn't. It goes. Okay, so some small exercises. Okay, or problems, yeah. So number 1. So first is, how many degrees of freedom a free particle has? Okay, so degrees of freedom of a free particle. Okay, by free I mean a particle on which there are no forces acting. Okay, it's just free. So how many degrees of freedom it has? 3. You need to tell me 3 numbers, x, y and z, or r, theta and phi, whatever you like, but you need to tell me at least 3 numbers and then only I will be able to tell you where it is. Okay, so that's 3. Now how about this? What are the degrees of freedom of a particle that is moving in a gravitational field? Okay, what do you think the answer is? So while I'm writing, you please think about it. So degrees of freedom of a particle moving in a gravitational field. And what do you think your answer is? I mean, this could be gravitational field of one planet, or let's say imagine there are hundreds of planets around sun, everything, and then this guy is moving. How many degrees of freedom it has? Well, the fact that there are forces acting on this is not going to change how many numbers you need to specify its location. It still remains 3. Right? I hope you understand that part. So degrees of freedom still remains 3. Another very simple problem. Imagine now you have 2 particles. Both of them are free. Okay? And they do not interact with each other. So 2 particles, non-interacting, there are no forces on them. How many degrees of freedom? So you think about it while I write the question. Degrees of freedom of a system of 2 free particles. Do you have an answer? Well, to tell where the first guy is, you need to specify 3 numbers. To tell where the second guy is, again you have to specify 3 numbers. So in total you have 6. Okay. So each one of them has 3 degrees of freedom times the number of particles you have, which in your case is 2. Okay. If I ask degrees of freedom of a system of n particles, clearly that would be 3 times n, and that will be 3n. Okay. Now what if you have 2 particles but they pull and push each other through Coulomb force, meaning the particles are not free but they are interacting with some forces, 2 of them. What's the degrees of freedom of this system? Well, as before, this interaction cannot change the number of coordinates you need to specify. It still remains 6. Okay. So degrees of freedom of a system of 2 particles interacting, let's say gravitationally or whatever force you like, it still remains 6. Okay. So usually students get confused when you say that there are certain forces acting on them, and then they may get wrong answers. Okay, how about this? Till now all our particles were free to move in space, and it was quite easy to answer how many degrees of freedom they have. Now imagine you have one particle, this we already talked, constrained to move on a specified curve. Okay. Then what? Then only 1. Because it's a curve, does not matter what the shape is. Okay. It's 1. You choose a reference point and you tell the distance along the curve you should go to find that particle. And that one number, the distance, is the degree of freedom. So that's 1. It's interesting to see that in a classroom, if you ask this question and you draw this curve and you say the particle is moving along this, quite a big chunk of the classroom will tell that this system has 2 degrees of freedom because they think that it's going up and down somehow. So it's in a plane and they will think it's 2 degrees of freedom. But no, it's 1. And you know why I'm saying 1. Okay, how about a particle constraint to move on a plane? If it is on a plane, let's say I put x and y coordinates system, then clearly the degrees of freedom will be 2. You can tell how much you should go along x, how much along y, and you'll find the particle. So 2 degrees of freedom. And clearly, if I take a surface, whatever the shape of the surface is, if it's a surface, again the degrees of freedom is 2. And why is that so? That is something you should think about, okay? Okay, I'll give you one exercise which you should try to do yourself, and we will end with that one. Yes. So here is an assignment for you. Okay. So find the degrees of freedom of a sphere, okay? Of a sphere constrained to move on a smooth surface, okay? So imagine you have a ball, okay? And this can only move on a smooth surface. Now pay attention to the word smooth. There is no friction at all, 0 friction. So you should first think in what manner this ball is going to move. Can it roll? And then you find out how many degrees of freedom you need to specify where that guy is, okay? Find the degrees of freedom of a sphere constrained to move on a smooth surface. By smooth, I mean frictionless. Surface. Okay, we'll meet next time and look at the solution of this one. Hopefully you would have done it by then. And we'll continue our discussion of analytical mechanics. See you.